Okay, so we're going back to Bridget Dynamics, and today we're going to be talking about applications of superposition. Um, yeah, today we're going to be focusing on the application, and we're not really going to be building a lot of theory today like we usually do in these videos, but nonetheless, yeah, we're gonna do some applications. So, just a quick recap: what exactly is superposition? So, superposition. So a quick recap of what superposition is. So superposition, not superposition. Um, so superposition is that if I have quantum states, so I have a certain indexed amount of quantum states. Now I'm gonna use capital psi. Uh, Quantum states for a certain object. So let's say this is like an indexed set of quantum states. So I in some index set J. Then what I'm saying is that the actual wave function of my quantum system is equal to the sum or the combination or certain linear combination. So alpha I times my index my index states. So this is what superposition is for, of course, alpha I in the complex numbers, or alpha and I part of the real numbers, the reals. So that's what superposition is, and essentially it's analogized with the cat in the box experiment or thought experiment by Schrodinger's cat, in which, right, we put a cat inside a box. We sort of modified this analogy for us. We put a femboy inside a room with a suit, a tuxedo or a suit, basically a masculine sort of apparel, and we also put a maid dress or a feminine apparel, and then we find out that we can't know definitively what he wore until we open the box, and because we can't definitively know what he wore inside that room, we assume a superposition, or we assume that he wore both of them at the same time until we open the box and find out he's worn either the masculine suit or the maid outfit. So that's superposition for you, or as a quick recap. So how I'd like to apply superposition right now is with random kindness. So those memes were in we have a guy and then like a girl or some other guy or whatever whoever sort of shows him random kindness, right? And he's trying to interpret whether it's the girl flirting with him, or it's just simply her being kind, randomly kind. And the thing is, we don't know what the true motives of that girl is. We don't know if she was really being flirty or if she was being just kind. So naturally, in a situation like that, we want to assume a superposition of both states where she was being kind and she was being flirty. So what I want to do is create or set up a wave function. I'll call it K, wherein this wave function represents the kindness, and I want to construct another wave function. I'll call it F, and it represents the flirtiness. So really, these guys, I want to restrict these guys between 0 and 1 inclusive. So they sit within a parameter space that somewhat looks like a square. So it will look somewhat like this. And this is sort of the measure of it. So this over here would be the wave function in K. You guys want K or F? I think I'll go with K. So this one goes in K, and this vertical, quote-unquote vertical one will go in F. So that's that. And sort of it will look something like this, or maybe like this, or maybe like a mixture of both, something like that. What matters is that we have two measurements that we could possibly make, and that's a measurement of the kindness and a measurement of the F. and the measurement ranges from 0 to 1, or you could say it goes from 0% to 100%. And in this case, 0 would represent sort of there is none of that measurement, and 1 means there is absolutely all of those measurements. So I can't just say that the girl was being 100% kind or not at all kind and being 100% flirty, or vice versa. The situation is much more complicated than that. It's much more nuanced than that. In the sense we're in, we can't only consider like four extremes, but rather it's a continuous sort of amount of states or amount of measurements of each state. So there's that. Oh wait, I'm sort of wrong. This is a bit of bad notation. This is a bit of bad notation. I'm gonna get the object. I'm gonna say the measure. So you guys already know what the measure. You guys already know what the measure function is. It's a function mu that takes in a certain input, and then it maps that certain input, and then it takes it to R, essentially, right? So I want my mu of my k. So my measurement of my mu, and then my measurement of, I'm just gonna say the square of the probability amplitude. So the measurement of the square of the probability amplitude, so would be ranging from 0 to 1. I wanna restrict that. And the measurement of the square of the probability amplitude of my flirtiness, or the flirtiness of the girl, will also sit within between 0 and 1. There, that's my proper notation. So so essentially we sort of have, we also want to add another parameter, although that might complicate our wave equation, our Schrodinger equation, a bit more, but it's actually a necessary thing, because what we actually want is that at a certain time the interaction happens between the guy and the girl, wherein the girl gives like this sort of thing to him, and then he tries to interpret it as the girl being flirty or the girl being kind. So we want in a certain point in time, we want that in a certain point in time, one of these measures spike, essentially. So we have this sort of curve at a certain moment in time. So apart from this parameter space we have over here, we have a different parameter space which I think is much better. And that's this. So let's start with a two-dimensional case wherein I only consider one of these guys. So let's assume that they're being like only flirty. They only want to flirt with a guy. So I have a certain point t. I have my time axis t, and I have my kindness, or I mean my flirtiness, or the measure of the probability amplitude of my flirtiness. So there's that. And actually it's just the probability amplitude, or the square of the probability amplitude. It'll be over here. So let's say that they were being absolutely flirty, like 100% flirty. Like the girl has the hots for the guy, and at that certain point in time where the spike happens, she just sort of gives him a random gift that's like hinting him, hey, I really like you so much. Like later I wanna fuck, like something like that, let's say. Let's say this is 1, of course this is 0, and let's say at time A. So obviously, since these guys are wave functions, they will have to sort of course, since they're wave functions, they have to satisfy the fundamental property that taking the integral over all R or all C of the square of the probability amplitude of these guys. So this could be F or this could be K squared, so dx. So whatever variable we put in there. So I'm just gonna put small x is equal to 1. So of course they'll have to satisfy this condition, and also the integral over all R of my kindness, or the kindness of the girl, square of that dx is also equal to 1. And obviously, they have to satisfy the Schrodinger equation. But the thing is, we have to do a slight modification to the Schrodinger equation, and we don't consider the time independent Schrodinger equation. So let's recall once again, like in every lecture, the Schrodinger equation, h bar squared over 2m times, I am gonna do this in sort of a formulation that rings with with general relativity, because we're not usually talking about x and y in the spatiotemporal sense, but rather we're talking about measures. We're talking about space in terms of measures of this and t. So really, our we're talking about directional derivatives in the time direction and in the direction of each of these measures. So I'm gonna assume that let's assume that this k is sort of a point in the square of the probability amplitude of my k wave function. And let's use f. So just f. So f without the the vector notation would mean a point in the square of the probability amplitude. So we'll call it those. So we're talking about direction derivatives here, so I'm not going to use the Laplacian operator anymore. So instead, I'll do it like this. So d by df, or if I want a notation that's more succinct, I would say x raised to the measure, so x raised to k. That's just a notation. It's just a notational thing. And then the partial derivative with respect to x and an f, wherein xk would be inside the probability the square of the probability amplitude, or the measure of the square of the probability amplitude of k. Of course, that would be ranging from 0 to 1 in the reals, or it would be ranging from 0 plus 0i to 1 plus 1i in the complex plane. They're just, those two are sort of like isomorphic structures, so it doesn't matter. So x f would range in the measure for square of the probability amplitude of the flirtiness. So there's that. And also time. So d by dt. Because yeah, you could consider the wave function in a sense where it conforms with the time independent Schrodinger equation, but the thing is, it's also important we need to consider time. So this is only one version of the Schrodinger equation for these wave functions. Okay, so there's that, and then plus I have my v, my potential, and then this is my x bar. And what I mean by x bar is it's the three dimensions that we're talking about here, which is xk, xf, and t essentially. But we would also consider t independently, so it could just be xk and xf. And so is equal to I h bar times the time derivative, so d by dt, and this is with the wave function. This is my wave function. I'm gonna do it blank because we're talking about either k or f. So this is my wave function. So I'm gonna write them explicitly down here. So h bar squared over 2m times d by dxk plus d by dxf plus d by dt times my f wave function plus the potential. So this is xk, xf, and then t times the wave function. So So the flirtiness wave function is equal to I h bar times the time derivative of the flirtiness wave function. So this is my first equation for the interaction. Squared over 2m. So this is d by dxk plus d by dxf plus d by dt of the kindness wave function plus the potential, so xk, xf, and then t times k is equal to I h bar d by dt k. So this is the first version of my Schrodinger equation. And now, so that's easier for you guys to solve the actual equation itself, what we want to do is impose what exactly are our conditions for the potential in this case. So considering the case a while ago, or the scenario I'm talking about a while ago, where in a certain time a equals t, the interaction happens, of course, I would set it up like I would here. So it would sort of look like a so it would look like a modified or finite form of the Dirac delta function, where at a certain point it sort of spikes, right? So I have the requirement that my potential v is then equal to 1 at t equals a, or rather it's a certain measurement, so it's the measurement of the square of the probability amplitude of my certain, wave function at t equals a, and it's 0 when t is not equal to a, so else. So in this case, v for my f would then be equal to a mu of the square of my f wave function when t is equal to a, at 0 when t is not equal to a, and the potential function for the kindness wave function would then be the following. It would then be the measure, you guys already know this, the measure of the square of the k wave function. That's square of the probability amplitude for the k wave function when t equals to a, and 0 when t is not equal to a. So when you guys solve the Schrodinger equation for this scenario, you guys will notice that you actually have to solve 4 of them. But the easiest to solve are usually when the case we're in, this vanishes, of course. The second case we're in, we're not in A, in which case it's probably gonna look something that's flat-ish. So now considering them both at the same time is a bit difficult, but you guys can consider the fact that since these guys are wave functions, any combination of them. So let's assume I have a wave function called kf. This is just notation, by the way. This is not like a multiplication or anything. We assume a double wave function, or a wave function containing k and f. So assuming we have a superposition of them, right? So what we can do is we can say that we can split this up into two sort of wave functions, k. So I'm gonna do something else here. I'm gonna assume I can split them into two functions, k, phi of xk and psi of xf. And from there, you guys can split this up. So I can plug this straight into the equation. So essentially, I can say kf in this case. Kf and kf. Okay. Alright, so I'm gonna plug this straight into the Schrodinger equation. And yeah. And since we already have this over here in the other side, I'm gonna ignore it in this case. Okay. So okay, here we go. So h bar squared over 2m times d by dxk plus d by dxf plus we also have a function of t, by the way. So we have another function, regular phi, or wait, no. I'm gonna say xi, or chai, xi of t. Okay. So d by dt. And then we, assuming that we can do this, we can separate them. I'll say that d by, so phi of xk, and then psi of xf, and then I have my psi of t, and then this is plus v of xk xf, and then t, and then I have my so phi of xk, and then psi of xf, and then my psi of t, and then that's equal to I h bar d by dt of this entire thing again. So phi of xk, psi of xf, and psi of t. Okay, so what we want to do next is notice that these guys will distribute onto the derivatives, so I'm going to do that explicitly. So h bar squared over 2m times, and next notice that when I distribute this onto the first derivative over here, the partial wave functions psi and xi will be able to factor out. So I can pull that out here. Psi of xf and psi of t, and then this is d by, oh wait, I'm so wrong. These are doubled. These are second derivatives. Okay, d squared, dxk squared, squared. Okay, squared. These are double derivatives. Oh, my bad. Squared. Anything else? Right. This is squared. Okay. Squared dxk squared. You guys are probably screaming at me about that already a while ago. Okay, next I can pull out my phi and xi functions. So psi, xi, and then screwing up in this lecture. Okay. So this is for phi of xk, and this is plus phi of xk times psi of t. This is d squared over dxf squared of psi of xf, and then plus of course next I will get to factor out my, in the sense, spatial components. So psi of xk, and then phi of xk, and then psi of xf times the second derivative, so d squared dt squared of my xi, and then that's plus the potential function xk xf, then t, my phi, I'll just shorten these guys, phi psi xi, and that's equal to I h bar. So I can pull out my phi of xk and my psi of xf. So this is phi of xk times psi of xf, and then times I h bar times my psi of t. All right. So what I want to notice next is that this IH bar, IH bar psi of t is simply the energy of my system, right? It's the energy of my system. And you know this from our original discussion of quantum mechanics, or rather in the book, our reference material. So I can say that this over here is equal to the energy E. And same thing here. This is simply the derivative of my energy E. So this here is the d over dt of the energy. But the thing is, E is a constant. The energy is a constant. The energy of the interaction is constant. So I can say that this is 0. So then, now, we actually do end up with a time-independent version of it. Quantum mechanics, people, quantum mechanics. Even though we said a while ago we have to consider the time, there will come a case wherein if we can split these up into individual wave functions of the time, the measurement of the kindness and the measurement of flirtiness, we end up with a wave function, a Schrodinger equation that's time independent. So, keeping that in mind, we can say that this is h bar squared over 2m of, so this is psi, and then d by dxk squared, so d squared over dk squared of phi plus oh wait, yeah, oh geez, okay, so is that, and then my phi psi d squared over dx f squared of psi plus my energy, which is 0, and then that's plus that's hot, plus v of, so the potential function, you guys will know that that's psi phi psi, it's equal to essentially the energy times phi of xk times psi of xf. So next we have this psi over here, this psi outside, so I can pull that out. So h bar squared over 2m of psi, and then this is psi d squared over dxk squared of phi plus phi d squared over dxf squared of psi plus the potential function times psi, and then that's equal to E times guys xk E of xf, and there. Now I'm gonna divide both sides by this psi, and you'll notice that this over here, this expression is essentially the product rule for the double derivatives of these guys. So I'm gonna divide out by this psi function, and we can just say that this is the d squared over dx, I'll say alpha squared of my psi of xf and my phi of xk, and this is plus the potential function times phi psi is equal to the energy divided by psi times phi of xk times psi of xf. And you notice that since E here is dependent on this function, this psi function. I can essentially say they're all part of a second energy constant. So that would be h bar squared. So my final in the time independent Schrodinger equation will be this. So d squared over dx alpha squared of my new wave function. So psi, small psi, plus the potential times psi is equal to the energy times psi. And so that's essentially, I'm saying that psi is that combination, or that partial combination of my phi of xk and psi of xf. What we essentially did was derive the time independent Schrodinger equation from this situation over here. Now the thing is, I believe I did some illegitimate things here, like dividing out by psi. First of all, this was not supposed to depend entirely on the spatial part here should not depend entirely on psi. The psi was supposed to vanish at some point here, and we would be left with just the energy on one side. But really, that's, you know. So simplifying further, we notice that, of course, this h bar squared over 2m times my d squared over dx alpha squared plus the potential function is equal to the Hamiltonian of the system. So I can essentially say the Hamiltonian of the wave function is equal to the energy of the wave function.